Thank you a lot. Hey, people, thank you a lot for coming along in this workshop. I'm Zvezdin Besarabov. I am a student at University College London. And today we'll be talking about everything blockchain, all things blockchain. And to the extent that we can talk about this in 1 hour. So first, a bit of background about myself. So I worked with blockchain for about 4 to 5 years so far. So I started about 1 year or a couple of months after Ethereum was founded. And yeah, it's been a pretty interesting ride. I've essentially made so many horrible investment decisions, including, let's say, somebody wanting to send me like $2,000 worth of ethers when ether was worth absolutely nothing, and I was like, no, because ether would could fall down twice, and then nothing could happen with it, right? And then it went up like 200 times. So yeah, good stuff. So don't come to me for investment advice, but maybe I might be able to teach you some blockchain stuff. So my most recent work has focused on designing a blockchain protocol for distributed machine learning. And something I'm working right now on is about a research of smart contract security. So that's about smart contract upgradability. Cool. First, before we even settle down on what this workshop is about, I just want to emphasize the importance of understanding blockchain. So Ethereum is one of the biggest cryptocurrencies right now. And back a couple of years ago, they created this thing called the DAO. So this was a blockchain application running on the Ethereum blockchain. So it was a crowdfunding campaign. So the aim of it was for anyone in the world to be able to chip in money, and then they would get to vote how this money would be used for the development of Ethereum as an ecosystem. So generally a pretty nice idea. The people who developed this also created a programming language and the virtual machine in which this whole thing is being run. Right? They created everything, and there was a bug in it. In fact, this bug was tiny, but it allowed somebody to simply drain the entire DAO. And this wasn't good because at the time this became the largest and biggest crowdfunding campaign in history. It collected tens of millions of dollars, people's money. And somebody just found a tiny bug, tiny visibility modifier of some function that essentially said whether that essentially allowed somebody to just completely drain this thing. So not good. Blockchain, understanding blockchain is important. So this workshop will be very theoretical. Essentially, I'll try to make it as interactive as we can. So please send as many questions as you can possibly think of in the chat. It's not just me. We also have two very, very, very helpful helpers here who will be able to assist with any kinds of queries. So don't worry. Just whenever something you feel like you didn't fully understand anything, just message us out, and either I or some of our helpers will get to it. With that said, I want you to also be very careful, to be very, very critical with understanding the concepts that we're talking about, simply because understanding blockchain, as we understood with the previous example, is important. And this is also a great preparation for another workshop coming in at 14 o'clock EST, which is entirely practical this time. So this will be about learning how to write smart contract code and executing it. So yeah, this workshop will be pretty interesting, and the one today will give you a really good base knowledge of how to adapt to the next workshop. Cool. So let's just get straight into it. So usually when we're talking about, let's say, a computer program, when we're talking about a relationship between my computer trying to use some digital service, we're usually talking about a client to server relationship. So we have this laptop, we have this server, they're communicating between each other. So that's a very traditional, very centralized way of thinking about the world. Now let's think about some questions. Who actually determines what data is accepted? So let's say my computer is trying to send some messages to this messaging server. So let's say this is the Facebook server or whatever else. So I just want to add some messages there. So I just want to add some data there. The server controls completely how, when, if, and under what conditions my message will be accepted, or it might just be thrown away, and nobody in the world will understand that I actually did this. And then if the server accepts my data and stores it there, it controls clearly who has access to it, who can read it, and who can modify it. So essentially, we do require a lot of trust and this setup. Whereas essentially, what blockchain is all about, and what I'm pretty sure, if you've read about a bit of blockchain, this has been made obvious to you, is that it just happens without this centralized intermediary. So it's just that if let's say if it is a messaging service, then my computer can just add this message to the rest of the messages, to the rest of the pile of messages instantly, without having to go through a server, without having to go through anything centralized. And in essence, this is how it works. Though it will be quite wrong to try to think about only two entities at this stage, because it isn't. So let's try to think about a very abstract case. So we're not thinking about a very particular case of, let's say, a messaging service or anything like that. We're thinking about simply data. So our computer wants to add some data to some collection of data. That's it. So we just have one collection of data, and we want to be able to add more data to it. That's it. So let's say this is a pile of data with some order in between. Cool. So what happens in a real blockchain is the value of a blockchain is all in replication. So let's say that we still have this pile of data, but this same pile of data is actually copied around, let's say, 4 computers in our case. So 4 computers have exactly the same pile of data. And what our computer wants to do, our computer is part of these 4 computers. Our computer, what it wants to do is it wants to add some data on top of this pile of data. The way that this happens is that this data is simply sent to everyone else participating in this network, which is a peer-to-peer computer network. And everyone else independently simply copies these data and puts it on their own pile of data, such that whatever happens, in the end of the day, everybody still holds the same copy of everything. And this is very fundamental, because while there are many complexities as to how exactly this could happen and how resilient is it to attacks, the whole point is that if you have something copied around many places, it is incredibly difficult to prove that this something didn't happen. Just like with the internet, but here it's a little bit more strictly defined. Once it's out there, it stays there, and that's the value of a blockchain. Now imagine that we're not just talking about 4 computers. Imagine we're talking about 4 million, 4 billion computers. Now we're talking about a completely different picture. Now imagine that I sent a specially crafted message. So not just some random data. I sent some particular message that, let's say, is cryptographically signed by my identity. So that means that if I cryptographically sign some message with my identity, that means that everyone in the world can easily verify whether a particular message is actually sent by me. And so if I cryptographically sign some message and I put it on this blockchain, which gets copied over absolutely everywhere, let's say everywhere in the world, then it pretty much means that nobody in the world can dispute that I actually did this, because they can see this message is there, I signed it. And well, it's copied around so many places that who would dispute it? Who could possibly comment and say that this didn't happen? So yeah, that's the fundamental value proposition here. So we can think of it as a different example as well. So we think about let's say like a hotel or a restaurant guest book, where after guests leave the place, they have this book that is completely open for anyone to write, and anyone can add stuff to it, and anyone can just do whatever it wants to do, whatever they want to with it. So people just come and write some random interesting stuff. It's kind of like that, except that nobody has ultimate control over the guest book, because in the case of a restaurant, obviously somebody owns that particular guest book. But let's say in the case of a blockchain, imagine that every person in the restaurant had a copy of the same guest book, and they synchronized what they write on their copies, so that it ends up being equivalent in the end of the day. That's essentially what it is about. Well, a bit more complicated. So let's talk about what blockchain gives us, and then let's get to the point of how actually blockchain gives us this. So what kind of guarantees do we have here? Well, first, we need the guarantee that anyone can participate in the blockchain. In our very oversimplified example, it means that everyone should be able to add data to the pile of data, which is actually a blockchain, but I'm just using pile of data because it's just easier to understand. So not only that is that anyone can see this pile of data. So that means if my computer wants to become part of this network of computers, I should be able to join in, and I should be able to instantly just copy whatever data has already been put there, such that my data copied locally in my computer is exactly the same as the one stored on every other computer. And another important guarantee is that nobody should be able to change what happened. So if something was added to this piece of data, nobody should be able to remove it. Nobody should be able to change it. Nobody should be able to do anything that the entire group of computers themselves don't want to do. Because let's say if the blockchain is written in a way that says, if like every computer keeps adding data to their pile, but if they get some very specific data, then they can interpret this data and then they can just do some other actions as well. That's fine. This is part of something called the blockchain protocol. This is part of like what do you actually do with this data? But it's not cool to try to do something different than what is part of this blockchain protocol. This might get a bit complex. I would just cover this with a couple more examples later. But I can see another question here. Does anyone own Bitcoins? I actually don't, and that's probably a bad idea. But we can see that there is a question: how is that the same to all nodes in the network so that it's synchronized? That is a great question, and we'll actually get to that just in a sec. In terms of how come do you actually ensure that everybody adds the same piece of information? And spoiler alert, there is no perfect solution to this problem. In fact, every way to solve this problem has major disadvantages. But let's just get to this. Let's just have a more practical example. Let's say of a voting system. Just to get familiar with abstracting things a bit less and making them actually a bit more practical. So let's say that in this case, we want to make a blockchain, but our blockchain will not just allow everybody to just add some random data to it. So that this data has to be very particular, very specified, such that not everybody can add any data. It has to adhere to some rules. And these rules are known by every computer running the blockchain. Okay. So let's say in this example, we have the blockchain, so that this piece of data is copied around all nodes. And we have Bob. And let's say we want to hold some elections. So that means that let's say we want to specialize this blockchain thing to simply hold an election. So that means that every computer here, they know how to hold that election. They know which rules needs to be true in order to do some stuff in this blockchain. Let me just give you some example in this case. So let's say that Bob wants to send a message to the blockchain that has the meaning I vote for Jack. And our blockchain, like I said, has particular rules. And let's say that it only allows new stuff to be added to it if they are votes, if they are valid votes. Now, what is a valid vote? Well, first, what happens is that Bob uses some computer because, well, everything starts with some computer which must be a member of this blockchain network. So this computer sends this data to everybody else. And then instead of just blindly adding it to the pile of data, here we add an extra step. They actually try to verify whether this data is valid, and then they add it to the blockchain. So what happens in this case is that they will check whether actually Bob signed this message. So let's say that we introduce some signing here. So people must identify themselves with some cryptographic way to prove that they actually are who they are, that this particular message was actually sent by this particular person. So first, let's say all computers check the signature. Let's say the signature is actually coming from Bob. Then they actually check the meaning of the message. So they try to check, okay, has Bob already voted already in the history? And because every computer has the same copy of the history of messages of votes, they can easily verify themselves. They don't need to talk to anyone else to figure that out. And so let's say that these checks pass. That means that, well, every computer does these checks independently, but because they have the same data, they will most likely also reach the same conclusion. Of course, this gets more complex exactly how this happens, but let's say that this happened at this case. And this right now is a completely fair election in terms of nobody being able to override it. Because, well, in order to override it, you need to take control over pretty much all computers, or let's say in practical terms, more than half of the computers. You need to take control of more than half of the entire network, and then you need to manually go and change their local data, because like I said, the value of a blockchain is in replication. So the only way to beat it is to remove the replication, which is pretty difficult. Cool. So where's the actual block from the blockchain coming from? Well, in actual terms, we're in practical blockchain scenarios, we're not usually talking about individual messages being verified and being approved by computers, because that's just simply inefficient. We have simply too many messages to deal with. So these messages are usually combined in big packages called a block. And then this block is being sent around and being verified and being added to the blockchain, just like what happened with individual messages before. So it doesn't really give us any fundamentally it doesn't change anything. It just makes the blockchain practically more useful. Cool. So let's just have a bit of a break here with us clicking around some blockchain explorer, and let's figure how things are with it. So blockchain.com, I would just also paste the link in the chat. So just click around this website. I'll be showing you some stuff, but might as well just go through it on your own. So blockchain.com, here we have a tab called Explorer. So what is a blockchain explorer? Well, like I said, the blockchain data is completely public. So that means there are many websites that easily allow you to visualize what's happening in a blockchain, and simply make things like easier for us to understand what's going on. So if we click on Explorer, for some reason my connection is very slow. Can you just confirm that you're still hearing me and everything's fine on the stream side? Yes, no, please. Okay, cool, good stuff. Okay, amazing. So a blockchain explorer simply allows you to see what happened in the blockchain. So here we can see a list of latest blocks, which is blocks get added over time as people want to submit messages to the system. So in the case of Bitcoin, blockchain.com is a blockchain explorer for Bitcoin. In the case of Bitcoin, one block gets added every 10 minutes. And a block has a particular number, so it's called the block height, which is simply the sequence, the index of that block within the sequence of blocks. Cool. So there is a lot of data around exactly how Bitcoin functions and around the cryptography around this that I'm not going to get into it. It's pretty interesting to dive into the rabbit hole exactly how blockchain works. In this case, I just want to point you to the list of transactions that have happened in this block. And let's say, and the fact that we can also click on a particular transaction and we can try to analyze it. We can try to see what happened, because, like I said, this data is completely public. So every transaction is identified by its cryptographic hash. If you don't know what's that, it's fine. And every transaction has essentially a sender and a receiver. So Bitcoin is simply a blockchain that tries to, again, interpret its messages in a very specific way. So in the case of Bitcoin, the messages must adhere to the structure of having a sender, having a receiver, and then having a particular value that is being sent around. So it's just like this message with two identifiers of people and then a value, kind of. Well, it is kind of that way. So yeah, in this case, we can see that this person identified by this account. So in most cryptocurrencies, accounts are identified by their public key. So this is simply some public identifier that we can use to actually check whether a particular message has been signed by a particular person that like the person who sits behind this identity. But anyways, in this case, this person is sending this amount of Bitcoins to two people, actually, two receivers. So this one is getting this amount, and this one is getting this amount. So yeah, nothing too fancy. Just a regular transaction with a couple of quirks as to, well, how do we actually ensure that this data is correct and things like that, which is why we have some more details here. But again, we don't have the time to get into these things later. It's just for you to start playing around with blockchain data and figure out essentially how things are going. Cool. Let's just get back to the slides. Cool. So let me also introduce you to another essentially view to well it's it's a pretty similar way to view blockchain, but I just want to introduce you to the idea of Bitcoin and essentially how does it function. So just like I mentioned about computers running servers and this being a very centralized model, it's essentially exactly the same with banks. So the reason why your money is valued is because some bank stands behind it. It says that this banknote here or this number in your balance actually means something. So if this bank didn't exist, then your money might as well be worthless, because without this bank, how could you know that, well, somebody couldn't just print out some fake money on by themselves and then try to fool people with this? So the whole purpose of a bank is to bring trust into this system. Whereas in the case of Bitcoin, it's trying to do essentially that thing, but without this intermediary. So let's see how it actually happens. So let's imagine that we have this spreadsheet. So this is literally an Excel spreadsheet. So it has no special connection to the real world whatsoever. Like, it's just some random numbers on a spreadsheet. Okay. So we have this spreadsheet that has the data of about 3 people on it. So we know that Jack, Bob, and Alice exist. We know their cryptographic identity. So they're these public keys. And I think somebody asked the question, are public keys linked to an IP address? No, actually, well, not directly. If you're trying to, if you're using a particular computer to send messages into the blockchain, then other computers obviously will know which IP address these messages are being sent from, because you have to use a particular computer to do that, and you have to talk to computers in a peer-to-peer network. So most likely, some part of these computers will know your IP. But by default, nothing that gets stored in the blockchain connects your real personal identity with your cryptographic identity. With that said, in practice, in too many cases, in order to even buy Bitcoins, you need to provide the government with your ID document and your cryptographic identity. So there are many mechanisms which are trying to force you to connect these two pieces of information. But Bitcoin fundamentally doesn't. Let me just see some other questions. How would I see the future of blockchain? Actually, remind me to answer this question about at the end of the talk, which is essentially when I'll be talking about this. So another question, which is actually very, very relevant to what we're talking about here: does Bitcoin actually have value because it's pegged to flat currencies? And actually, no, not even close. And that's the value of a blockchain. Bitcoin is not pegged to absolutely anything. So let's just look at this spreadsheet. So this spreadsheet says three cryptographic identities have some random number to it. This it has no relation to the real world. It's not pegged to anything. It's just some random numbers on my Excel spreadsheet. Okay. So what happens? Let's just use this spreadsheet. Let's say that we have these 4 computers again. Let's say all of them know about this spreadsheet. So all of them know about the contents of this spreadsheet. And let's say we're trying to make a currency. So we have Bob. Bob wants to send some 5 Bitcoins to Jack. Well, let's say not Bitcoins, 5 numbers, 5 whatever. It's just a spreadsheet, right? It's not a currency, right? So we're just moving some numbers around in the spreadsheet. So let's say Bob wants to send this message, and let's say our blockchain is written such that a message can only be accepted by a computer, but by a node if it's coming from a real person. If it's coming from somebody who signed this message. So like if the identity of this message can be proven, then what happens is that the nodes in our blockchain are trying to interpret this message. So let's say that this message is structured as something that says, take 5 out of my cell in the spreadsheet and put 5 into Jack's cell in the spreadsheet. So let's say that this message has this meaning, this functional meaning. So what's going to happen is that first we need to check, does Bob actually have 5 in the spreadsheet? Because if he doesn't, then we shouldn't be we shouldn't allow them to actually do this. let's say that they do, because in the spreadsheet we saw Bob 15. Cool. So this message is accepted. It gets added, and then all the computers at the same time are also updating their local copy of the spreadsheet. So they're saying Bob 10, Jack 5 now. And well, this is all what essentially what Bitcoin is all about. There is nothing more fundamental than what I essentially just told you. And the reason why this creates value is because there are very specific rules as to how you can move numbers around in this spreadsheet. You cannot create numbers out of thin air in this case, in this oversimplified example. You need to already have them in order to send them, right? And if you send, then it gets received. So it doesn't get lost anywhere. So the amount of let's say Bitcoin in our example stays constant, stays the same. So that means that essentially people can trust that these rules will be enforced because they will be. This is what the blockchain is about. It's all about enforcing these rules using this replication principle. And what essentially happens here is that, well, if let's say we have a startup and this startup says, we can accept payments in these Bitcoins, right? So that means that, like, essentially, somebody might actually be willing to exchange real money for or Excel spreadsheet numbers here, just because this particular startup sells their product using these Excel spreadsheets numbers. And you see where I'm going with this. This actually starts to be some currency which is valued because it has some practical uses, because people actually want to hold it, because people believe that it will be, because people believe in the rules that they are that are enforced in the blockchain system. And well, that's what blockchain is all about. So essentially, this is how Bitcoin creates value. It's not because it's pegged to any real cryptocurrencies. Now, we have some other cryptocurrencies which are actually pegged, so directly connected to the dollar or something like that. Bitcoin isn't, and that's the beauty of decentralization. I hope that answered your question. Let me just see on any other questions. Anything can only have value if others value it. So yeah, essentially, if people want to use it, and people want to use it simply because they trust its rules, and because, let's say, that there's some practical application to this. Let's say that I can send however much money I want just to my friend in Iran, whereas, for example, let's say my bank would charge me like 30% commission because, let's say, they don't want me to do that or something, or they're just abusing their power. So you see how people would like to use it. So what does that mean? The number of Bitcoin is limited in the world. So in the real scenario, actually, yes. The number of Bitcoin is not constant. It's continuously increasing. But the way Bitcoin works, there's actually only 21 million Bitcoins that will ever exist in the existence of Bitcoin, because these are simply the rules which were set in the Bitcoin blockchain. And yeah, so that's one of the reasons why the Bitcoin value keeps going up, simply because, well, people know that it's a limited quantity. For example, in Ethereum, there aren't hard rules that say that limit the number of ethers, but people would still buy it still, because even though it's not a limit, it's not a constant supply, but it still is. There are still some very particular rules that say exactly what happens with the currency. Can you mine other coins too? Yes, and I'll tell you how to mine Bitcoin as well in just a bit. How do I distinguish between a fake and a real transaction? That's a good question. Simply put, the blockchain that you're making needs to specify the rules that that needs to be true in order for some transaction to be accepted. So in the example that I just showed here, I said one transaction is valid only and if only it's coming from only if it's signed by somebody. So I can know the cryptographic identity of whoever signed this, because, well, I can then use that identity to come back and check some other stuff, like, let's say, their balance in the spreadsheet. And so you can't really sign. So cryptographically speaking, the way asymmetric cryptography works is that you cannot really create a transaction from the name of somebody else. So I can't just say, send me some of me, Bill Gates, send some 5,000 bitcoins to Zvezdin. That doesn't work. Simply cryptographically speaking, I read upon it because it's pretty interesting to see, mathematically speaking, how this actually happens. But yeah, I hope that answers your question. What are the advantages of block size? Do I think a bigger block size is better or worse? I feel like I haven't explained enough things to answer this question properly so far. But overall, so block size is so what Chris is referring to is essentially indirectly the number of transactions which are allowed to enter to be in the block at the same time. And so this obviously has to be limited because computers have to kind of quickly send around these blocks and have to verify them and things like that. So it shouldn't be 10 gigabytes, right? So there is a very hard limit on block size. And I think the cryptocurrencies are hitting this limit already. Like they're essentially making the blocks as big as they could possibly be, and they're still not scaling well. And I'll get to that in just a sec as to essentially what's the scalability problem in blockchains coming from? And that's actually a pretty interesting thing. So I will move on. I see a couple of other questions, but let me just try to get back to them a bit later because we might not have time. So let me just get back to essentially exactly one of the questions earlier on, which essentially asked, how do you synchronize everything here? And in fact, it's a really complicated question because let's just imagine that in the previous example, as I always said that we only had one person proposing a message that has to be added to the blockchain or a block, whatever. But in a real scenario, we don't have a hierarchy of like only one person doing this. Usually, we just have essentially everybody trying to send messages at the same time because the blockchain has many users. So we reach this fundamental problem where pretty much everybody wants to send something. So how do you pick which one goes first? Because you have to pick something, and all of the computers in this blockchain network must unanimously make that decision. Because, if they don't, if half of the network chooses something, half of the network chooses something else, then we get something called a fork, which is essentially two completely separate networks which are starting to develop because they have alternative versions of the blockchain, so they are starting to branch out in different potential realities or whatever. So this is what we don't want to happen. So who do you pick first? That's actually really difficult. And there are a couple of other questions. It's not just who. It's let's say if there are particular rules that say like pick the transaction where if you hash it, it starts with the lowest number. For example, there could be a check like this, and you can easily implement this, and then you can say, the consensus problem is solved because I can easily take a look at all the transactions which I need to add, and I can easily hash them and see which number is lowest, and then I can simply compare it in that way and add them in this order. But then we also need to take into account that people must not be able to influence that decision. So that means I should so if Bob and Alice want both to send a transaction, Bob shouldn't have an advantage in getting their transaction before Alice. So Bob shouldn't have a guaranteed or a likely way that they can cheat the system in getting their transaction in the list before Alice, because there are many cases where this simply breaks stuff. But the fundamental thing, which is the problem here, is that we don't want people to influence the blockchain in any way, shape, or form. I can give you many practical examples of why that's a bad idea, but essentially we don't want people to be influencing any of that decision. And in the same way, we also don't want people to be influencing what already changed. So what has already been added to the blockchain. So because we want to keep the rule, if something has been added to the blockchain, it stays on the blockchain, and we need to our consensus algorithm needs to guarantee that this is the case. And there really isn't an easy way to solve this. But let's just see a couple of examples of, for example, what Bitcoin is using to solve this problem, but this will be very brief because we have a bit more material to go through. So let's just say that so far, one practical blockchain is comprised of three main elements. So first, we need a networking part. So we need a way that the computers can actually form a peer-to-peer network that they can actually communicate to each other. And like you cannot simply DDoS some other computer and make them go down, or you cannot easily cheat the system by spamming stuff. So this is something that is easier. This is something that doesn't get changed between many blockchains. It's something that many people have already solved to a great extent, and we have good solutions to this problem. So this is not really the way blockchains differ. The way blockchains mostly differ is in the two other parts. So first, what I mean by an execution engine is essentially what are the rules that this blockchain must adhere. Because if you have no rules in a blockchain, then this blockchain has no practical utility. So there must be some way that you interpret these transactions in some particular way. You need to have some rules that say what makes a valid transaction and what doesn't, and you need to have some rules that say if some transactions is added to the blockchain, what does that mean? So, for example, if Peter receives 5 Bitcoins, then that means that Peter now has the capability of using that 5 Bitcoins, for example. So, and the third part is obviously consensus. Consensus is essentially the most difficult problem to solve because, well, it is a fundamentally broken thing. No, not broken, fundamentally simply a big challenge. Let's see how Bitcoin particularly does it. So in Bitcoin, I already gave you a couple of examples. So I presume that you can already realize you can already have a guess as to what are the rules of Bitcoin and what essentially happens with it. So let's say Bitcoin simply allows you to move these numbers in the spreadsheet around in a very abstract sense. That's literally it. Nothing too special. Move these numbers in the spreadsheet with very specific rules that guarantee that the number of supply in Bitcoin stays the same, etc., for example. And we also have, as a consensus, this thing called proof of work, which is essentially the simplest way that blockchains are solving this problem. It's also a very bad way in terms of scalability, but it is a very secure and very simple way. So if I had to summarize it in only 2 minutes, and it's fine if you don't understand it, but I'll just try to shoot it for just in case. So what happens is that in Bitcoin, people keep sending transactions that they want themselves to include in the blockchain left and right. So every computer essentially knows about all the transactions which people want to be included in the blockchain. They're not included yet because we need to package them specifically with a particular order, and we need to synchronize them. But essentially, every computer kind of knows most of the transactions which should be executed. So what happens is that every computer, or most computers actually, are trying by themselves to create a block meaning a combination of these transactions, because they know most of the transactions which people want to be executed because they're being sent around. However, there's a very specific rule that chooses which block out of all blocks must be chosen, because, well, everybody can just package transactions and make a block, right? So which block do you pick now? And here's an interesting bit. So the block you pick is the first block that you see that when you hash it, it starts with, let's say, 10 zeros. This is pretty much it, kind of. So the reason why that works is it's actually incredibly simple, but incredibly well, is that cryptographic hashes are really random. So you don't really know what data you need to hash in order to get some particular hash. So what happens is that people mine it. So people keep trying to make blocks and blocks with different data inside of them until they find a block that starts with, let's say, n number of zeros. And at this moment, they send this block like hell around the entire blockchain. And everybody tries to verify this because hashing a block is really, really easy, really quick. So people just send it around, and yeah, this block starts with n number of zeros, and they just accept it. And this is essentially how you solve this problem, because it's incredibly unlikely that at the same time one computer will see two blocks which when you hash them start with that many zeros. And even if that happens, there are also some mechanisms how to solve this problem, so it's fine. So yeah, this is literally what proof of work is all about. Okay. So let me just introduce you to Ethereum as well, as just simply an alternative perspective, an alternative take to blockchains. So far, we've only been talking about money transactions, and this is essentially the most hype around blockchains. But like I told you, blockchain fundamentally has nothing to do with money transactions. It's all about replication and running the same rules everywhere. And let's see how Ethereum is actually using this principle to create something completely different. So what is Ethereum? Ethereum is trying to become a blockchain where you can upload application code to it, and it can run that code in the blockchain. So what happens is that you send a transaction, but that transaction includes actually the compiled code of some program you want to execute, literally. And once this code gets added in a block, and once this gets synchronized around the blockchain, what happens is that, well, the computers simply execute that code because, well, that's what Ethereum tells them to. That's what the rules of Ethereum tell them to do. It's simply every computer in the world gets to execute exactly what your code said. And that's really good because, well, you can write any kind of tiny application like a voting system, for example, where instead of making your own blockchain for it with like the example I said earlier, you can just write a small script that you just upload to the Ethereum blockchain, and it gets replicated around, so you get the benefit of having a blockchain without making your own blockchain, essentially. And you also have quite a few other benefits as well, like a big ecosystem of different programs communicating between each other and things like that. But fundamentally, Ethereum is all about creating a blockchain. is all about you using the value of a blockchain without making your own blockchain, fundamentally speaking. And they also use proof of work as a pretty much the same consensus algorithm as Bitcoin. Now let's take a look at some of the disadvantages of this. First, before that, let's open Etherscan, which is Ethereum's blockchain explorer. So it's going to be a pretty similar interface to what you saw in the blockchain.com. Just that here we can see a couple of differences because, well, the transactions in Ethereum have a different meaning, and yeah, it's generally just a bit different, but fundamentally it's still the same thing. So yeah, latest blocks. Let's just open a block. Yeah, we see a lot of complicated things, but the most important thing, we see 177 transactions. Now, let's say that I want to take a look at this transaction. Right? Why? Well, because this transaction is actually not going to a real person; it's actually going to a program. So, in fact, this is a normal account on Ethereum, just like these cryptographic identities I told you about in Bitcoin. But the two here is actually something called a contract. So once you upload a program on Ethereum, it actually has its own identifier, and it doesn't get just and it stays there forever. So you can always use that identifier to interact with the program. You can send some data to it. You can call some functions. You can do whatever you can with just a normal program. And it becomes really interesting. In fact, I think that we can take a look at this contract here, and here we have a contract tab, and I think that we can actually take a look at the code of this contract because, well, like I said, the blockchain is public, so essentially you can just analyze everything. So yeah, we can see that this is simply a normal computer code here. Yeah. It might be too much information to take in. I hope that I'm not overcomplicated things, but please do ask some questions if you think that I haven't addressed something well enough. There's a question: as the network load increases on known blockchains, will servers costs increase? What do you mean by network load? As in, the more people use the blockchain, the more the cost of you, let's say, using the blockchain would increase. In fact, essentially, yes. Let me just get to that on the next slide right here. Ethstats.net actually gives you real time statistics of the running Ethereum blockchain. So it just gives you a bunch of geeky screens that you can open it and you can look like you're cool. Though other than that, again, this has a bit of details. But just to give you a particular example, essentially, because proof of work has fundamental limitations, it cannot create blocks really quickly. So with proof of work, you cannot really go much faster than, let's say, creating one block every couple of seconds. In the case of Ethereum, it's about 13.8 seconds. A couple of years ago, it was about 16 seconds. So they managed to make it just slightly bit faster. But when you lower that number, you start getting many conflicts in the network. So when you lower that number, that means that, well, it's essentially what this block time is all about is that there isn't any hard-coded timeout. Like in proof of work, when I explained it to you, I didn't mention the concept of time at all, and that's because the way you make this time is essentially by defining how difficult is it to find a valid block. So a block with n number of zeros. So as long as you change n, then that means that it would if everybody in the network is trying to find the solution to this task, on average, like let's say one computer will solve this problem in 15 seconds. In Bitcoin, it's going to be every 10 minutes, and this n gets adjusted so that it's always around 10 minutes or it's always around 15 seconds. Because if you make it much faster, it becomes a problem. And that's because, and therefore you have a strictly limited number of transactions that you can actually execute in a blockchain. And because of this, in fact, the more people wanting to use it, well, it's a supply and demand curve. So many more people want to use it than are able to use it. So that means that essentially those who get to use it should pay higher transaction fees, for example. Let's just introduce the concept of transaction fees. So in order for you to increase the likelihood that your transaction gets included in some block, you have to pay a transaction fee. And so the people who the computers who are creating these blocks, they get to choose which transactions they include in the blocks. So they can just choose the transactions with the highest transaction fees, because the rules of Bitcoin and the rules of Ethereum says that if you as a computer manage to create a valid block, manage to find one, which as I said, it's really difficult, you get to win all the transaction fees which are included in that block. And that's a pretty good incentive for people to compete. So yeah, blockchain scalability is a problem for real life applicability of blockchain systems in general. Another question: what does the code that people put in these contracts usually do? And in fact, it can literally do absolutely anything. Usually, it's actually creating its own cryptocurrency by itself, because like I said, this is simply a computer program being executed in a very trusted way. So that means that as long as I simply simulate an Excel spreadsheet, and as long as I add some functions in this program that say how can you move numbers around in this spreadsheet, this literally becomes a currency, just by the same way that Ethereum and Bitcoin is our currency. So the most common smart contract that you will actually find on Ethereum are actually currencies by themselves that particular startups are using to let's say they're trying to use it to raise funds, and they're trying to use this particular currency for their own product. Cool. So this is the last slide, and we have about 5 minutes left. With that said, I will give you a general outro of the future of the future of blockchain, and then if you guys want, I'll stay around for more questions or essentially anything that you would like to ask. So, like I said, fundamentally, consensus is the biggest problem of blockchains, because, like I said, right now it's just simply not scalable. Proof of work is very secure. It is very secure. It's not perfectly secure. You have, in some cases, you have cryptocurrencies which have been attacked successfully by a single person who managed to fool the consensus algorithm. But generally, it's very secure. And what we're seeing here is that many other next-gen blockchain projects are trying to create alternative versions of a consensus algorithm, which usually they're trying to make things much more complicated than proof of work is, because they're trying to simply work around these fundamental limitations. Usually, what we're seeing is that blockchains are trying to increase the compromise of security versus scalability. So they're trying to make it more scalable, more fast, more reliable, more usable, versus making it significantly less secure. It seems like this is a fundamental limitations of blockchains, at least right now. That, well, nobody has essentially found a way to have a blockchain that's both very secure and incredibly scalable. Because, well, if they did, then we wouldn't be seeing all of these alternative blockchains which are all trying to do a different thing. Something I want to point out, you have to take a look at Tendermint. They are using a consensus algorithm called PBFT. It's very interesting. It definitely sacrifices security for scalability, but it's a very interesting way of looking at consensus algorithms without the concept of mining. And Tendermint is also by itself a framework that allows you to create your own blockchain very easily. So it just gives you the consensus and the networking parts of a blockchain, and then you just get to write down how do you actually interpret these transactions, what meaning they have, what rules must be completed. And so it's actually incredibly simple to make your own, like your own brand new blockchain using Tendermint. And also I want to point out Polkadot as well. Polkadot takes a completely different take on consensus as well. In fact, Polkadot tries to create essentially a network of tiny blockchains which are all connected by a big blockchain. And in fact, they are trying to make it so that this big blockchain actually provides the security and the consensus that these smaller blockchains need to run. And it's a pretty interesting way to also think about blockchain. I think these are the two projects which are easiest to get to and show you to completely different sides of a way to approaching the blockchain problem. With that said, I'm very happy to have seen you here. We are just 3 minutes before the time limit. With that said, feel free to first message me on Discord. So if you take a look at the hack pack or syllabus of this workshop, you will see my Discord tag because I forgot to include it here. Sorry. And you can PM me directly on Discord with whatever questions you have. Also, please, on Discord, you can join the blockchain channel by ticking one of the options you will see it in the Discord. I'll be monitoring this channel throughout the day. If you have anything to talk about or ask, do reach out there. You can also contact me on these links as well. And right now, I'll just try to get through any questions that I haven't gotten through so far. You guys can feel free to leave if you have other commitments. But yeah, if you have other questions, I'll stay around for a couple more minutes. And hashtag blockchain is the channel. Yep, go there. Cool. Have I missed any other questions? So can I explain the difference, pros and cons of proof of work versus proof of stake? Yeah. So essentially what proof of stake is trying to do is so first let me just try to introduce proof of stake as a different consensus algorithm. So proof of stake is an algorithm that tries to solve the problem of proof of work being too energy hungry. In fact, Bitcoin right now uses more energy than a big part of, I think, most countries around the world are using individually, not in total. That would be like too much of a waste. So yeah, having all these computers crunching these numbers and mining the right block is very tiresome. So proof of stake is something that makes it a little bit more complicated as a protocol, but also allows you to essentially figure out how do you actually choose which block comes next. So proof of stake tries to say this: okay, not everybody has the right to create a block. Only one person has the right to create a block, and we have the entire network has an easy way of figuring out who is the person who has the right to create a block right now. And the way that people can actually invest in creating a block, the way people can actually increase the probability of them being selected to create a block is by staking money. So you have so everybody has a balance in this cryptocurrency, right? So they stake it. So they stake some part of their balance. By staking, this simply means locking up in some secure place that essentially they cannot access them until they unstake it. So they just stake it, meaning that they have they have skin in the game. So like they have invested in buying this cryptocurrency. So they're most likely looking they most likely don't want to mess up this cryptocurrency, because if they do, then the value of their own stake would of course go down, because well, if you destroy the entire currency, then your currency is also like your holdings of it are also most likely ruined. So in this case, so what happens? People stake, and then everybody knows how much everybody has staked, and so we run a little bit more complicated, mathematically speaking, algorithm that selects randomly speaking from anyone else in the from anyone in the list of people who have staked. It just randomly selects one of them, and the bigger your stake is, the more likely it is for you to be selected. So once you're selected, you have the rights to simply create a block. So you just create some block. You don't have to mine it. You just literally take some transactions, you put them in a block. You put your signature on this block so that people can know that like this block was actually created by the person who was selected, and then everyone will just accept your block. And the reason why this should be fine is because as long as you don't get one person having the highest stake in the system getting all the blocks, if this doesn't happen, then it should kind of be fine, because different people create different blocks, so they usually don't have an incentive to censor transactions, to mess up with the blockchain and things like that. But again, proof of stake has also problems. In particular, it has quite this problem with wealth inequality, which is essentially what we see in the real world. That essentially we have a very small select few set of people who actually have incredibly high stakes, and essentially it's you start to depend on them a little bit more, which is essentially what you really don't want to happen in a blockchain environment. So I hope this actually addressed proof of stake, and I hope this addressed your question. What wallet do I recommend? Actually, I don't. Maybe I'm just a geek, but I'm trying to run things locally. So I'm not really trying to use any kind of particular service that stores my crypto and host essentially has some sort of access to my crypto. So what I want to have is I want to have a complete full blockchain node on my computer, and then I want to also store the private key of my account on that blockchain on my computer as well. Of course, in most likely in an encrypted way. So that means that the moment I want to send a money transaction, what I do is I simply just start this local blockchain node. I let it synchronize for a bit, because to catch up with everything else that has happened to the blockchain, and then I can simply send some transactions directly through it. So I don't have to use a third party service, because what usually happens for convenience sake, instead of what I just explained to you, is what some wallets are doing is that you don't actually host a full blockchain node on your computer. You only hold the private key of your account on your computer, but you use somebody else's computer to send the transactions and to view your balance and to interact with the blockchain. So and then you have to trust that one other person who runs this computer or this server or whatever, that they're actually giving you a realistic view of the blockchain, that they're actually that if I'm actually sending a transaction, that they're not censoring that transaction. Because if they are the interface between me and the blockchain, then they can block transactions. They can just decide, you're not sending this transaction. So I simply don't agree with this centralization here. But so in this case, I don't really have anything to recommend in using this as a service. Okay. Discord channel. And what do you think of XRP's consensus algorithm? So I think I've essentially long forgotten what XRP is about. Sorry, I've read about it, but I don't really remember much to comment on this. I just have to brush up on my knowledge here. Yeah. Does anyone else have any other questions? Let me just put a final poll to see how the workshop was. So yeah, can you just answer this poll right now? If you still are here, I think we have about 16 people still here. Yay. Okay, so maybe I overcomplicated some things because yeah, no, I presume not everybody understood the stuff I said, but as long as you got the first half, like the general abstract presentation of fundamental blockchain, that's essentially all you need, because you can just brush up on the specific knowledge for any particular blockchain just with any kind of documentation material, as long as you get this fundamental concept that it actually took me quite some time to understand, which is essentially what defines a blockchain to be a blockchain. Cool. In which case, I am very happy to have you guys here, guys and girls and everything in between. And yeah, please do attend my other workshop later today, and where essentially I'll be showing you how to write a smart contract right now, as in like essentially today, and how you could possibly even integrate it into your hackathon project. And yep, otherwise I will stop sharing, and yeah, I'm very happy to have seen you here, and yep, have a great day, and good luck with the hack.